Okay, as promised, how long does it take to get to equilibrium? Okay, well, the equilibrium position is what? What's the value of y of t at equilibrium? Well, the equilibrium position is the y equals 0 position. Y of t equals 0. Now, you should pause and solve y of t equals 0. Okay, now if you weren't able to do that, hint, you're going to set this expression equal to 0. So if you haven't done that, stop and do it. Okay, you should have done it. We get 12 centimeters times the cosine of 6.3, I'm going to write the units, radians per second, times t, plus 0.8 radians. And that should equal 0. Well, that, of course, that implies that the cosine of this .3 radians per second plus t plus 0.8 radians equals 0. Okay? Well, when does the cosine equal 0? We could take the inverse cosine. You know, this should equal the inverse cosine of 0. The inverse cosine of 0 is 90 degrees, pi over 2 radians, but that doesn't give you the complete information. Okay, it's going to be that plus a multiple of pi. So that cosine, and let's think about it in terms of the unit circle. Okay, we're starting here at t equals 0. And we're going to move around the circle until we get to a point where the y is 0. Now this is y, it doesn't look like the y-axis, but not going to worry about that. If you really want, you can go back and call all these y of t's x of t if you like. Doesn't matter what symbol we use for it. It has its meaning, and we're just going to go on with this equation. The point is that the cosine is going to equal 0 when the argument is here or here. So at this point, cosine of this whole thing is 0 if this whole thing equals pi over 2, or any pi over 2 plus 2 pi. Now what's that mean? It means we're here when the argument, the 6.3 radians per second times t plus 0.8 radians is 0, or when it's 0 plus 2 pi, because 2 pi just brings us around to the same point, or plus 4 pi or 8 pi, etc. So we get cosine of this thing is 0 at this argument equal pi over 2 plus 2 pi times n, where n is an integer. Okay, and it could also be a negative integer. Maybe this thing's been oscillating for a while, and it was here at earlier times. Also, cosine of the thing equals 0 if the argument is 3 pi over 2 plus 2 pi times n. I write that as 2n pi. Okay, well, really all we want in order to answer the immediate question is how fast is it going at the equilibrium position, and that's going to be the same at all positions. Okay, and of course we're doing an ideal model. We're ignoring the fact that this oscillation is damped. If it was a perfect rubber band, we would come down to somewhere in this neighborhood and then bounce up to the same distance and so forth, and that's what this model gives us. The motion in the case of an ideal rubber band that doesn't damp out any of the energy. Okay, so what's the solution? Well, first of all, we're just going to use the pi over 2, okay, because that's the angle at which this thing first reaches equilibrium. So we first reach equilibrium when this quantity in parentheses, which I'm now going to write out, the argument of the cosine function, 6.3 radians per second times t. I was going to write theta naught, but it's 0.8 radians equals 0. Well, it's very easy to solve that for t. Okay. And I said equals 0. It's not equal to 0. It's equal now to pi over 2. And that's pi over 2 radians. I don't have room to write the radians. To be consistent with having written it over here, I should. But we solve this for t. And we get 6.3. Now I'm going to divide out the radians, but we still have the inverse seconds times t plus 0.8 equals pi over 2, and that's approximately 1.57. We get t equals then 1.57 minus 0.8 is 0.77 over 6.3 inverse seconds, and that's going to equal what? That's going to equal, I'm saying, about 0.12 seconds. Okay? Now you can check my arithmetic. I'm doing these things in my head as I go, but I think that's about right. Okay? Yeah. I'll kind of stick with that to the nearest hundredth of a second. Okay, so you see how we can solve for when this oscillator reaches this position. Now we could also solve for the next time the oscillator reaches the equilibrium position, which would be down here, and then the next time, which would be back up here, but we'd have plus a 2 pi and all that stuff. Not going to do that right now. I'm going to go to some other questions. I just point out that that's something you should do, and that's something that should be covered pretty well in any engineering preparatory pre-calculus course. Okay? It's a pre-calculus analysis, solving an equation of this nature. And hopefully you encountered that, if not in pre-calculus, in calculus, and if not, well, you're encountering it now and you're going to have to deal with it. Okay, well, we'll go on to other questions in a minute.